Hello everyone, my name is Stratis Varzakakos and today I will be presenting the paper CarFormer, Self-Driving with Learned Object-Centric Representations, authored by Shadi, Hamdan and Fatma Güney from Koç University. This work was presented at ICCV. CarFormer overview. To give you a quick high-level overview before we dive deep, CarFormer is a novel architecture that tackles the problem of scene representation in autonomous driving. It moves away from heavy static maps and instead uses transformer backbone to process slots, which are learned object-centric vectors that capture the world's dynamics. So what motivated this work? Currently, the dominant representation for self-driving is the bird's eye view grid. While effective, BEV maps are extremely high-dimensional. If you look at a typical map, the vast majority of pixels are just empty road surface. Computing valid driving decisions from this sparse pixel-heavy data is computationally expensive and inefficient. The goal of CarFormer is to prove that we don't need these heavy pixel maps or rigid manual attributes. Instead, the authors propose a learned, self-supervised, object-centric representation called slots. The hypothesis is that these slots naturally capture necessary driving information, like speed and heading, without us ever explicitly teaching the model those concepts. Related work from pixels to learned slots. Let's look at where this fits in the research landscape. First, we have scene-level representations, like standard semantic segmentation in bird's eye view. As mentioned, these are inefficient. Second, we have object-level representation, using explicit attributes. The state-of-the-art here is a method called plant-T. Plant-T discards pixels and represents cars as vectors of exact number, position, and size, heading, and speed. While efficient, plant-T is rigid. You have to manually define what an object is and exactly which attributes matter. CarFormer argues that learning these attributes is better than defining them. Self-supervised object-centric representations. To solve this, the paper builds on SAVI, slot attention for video. SAVI is a method that takes a video and decomposes it into slots or bottlenecks. It tracks objects over time without any supervision. Ideally, one slot learns to track one car. Until now, this was mostly used on simple synthetic datasets. CarFormer is the first to apply this to complex visual dynamics of self-driving. Transformers for SQL modeling. Finally, this relates to decision transformers. Typical transformers in robotics try to discretize everything into tokens, treating driving like a language problem. CarFormer takes a different approach. It uses a hybrid input mixing discrete tokens, like traffic light status, with continuous tokens, the slot vectors. This allows it to model complex decision-making without losing the precision of continuous values. And now for the technical part, and let's describe how this whole system works. So let's first start with SAVI. The architecture is a two-stage pipeline. The first stage is a perceptron using SAVI. As we discussed, the problem is that scene-level and explicit object-level representations are limited. SAVI solves this by compressing the world into a small set of vectors that implicitly contain the car's position, heading, and speed. SAVI workflow in detail. So, let's see how this works. Input. We take a sequence of ground truth maps over time. Then the encoder, which is a CNN that extracts visual features. And then we define slot attention, which is the core mechanism. It uses iterative attention to group these features into k number of distinct slot vectors. And now for reconstruction, the model is trained to decode these slots back into the original images. This reconstruction loss is what forces the slot to be meaningful. To reconstruct a moving car correctly, the slot must capture its position and velocity, even though we never explicitly gave it those labels. Here is a diagram that visualizes this process as used in the paper. The input BEV sequence on the top left is encoded into slots. Then the decoder on the bottom attempts to reconstruct the original video. In the final CarFormer model, we freeze this encoder and just use the extracted slots as our input tokens. The transformer. So for stage 2, the transformer is the backbone of this process. This is an autoregressive model. It takes a trajectory of tokens, including the SAVI slots, the target destination, and traffic lights, for example. It serves two purposes. It drives the car and it acts as a world model that predicts the future. However, standard transformers have a problem. They process data sequentially. If token A comes before token B, token A cannot see token B. In driving, this can be fatal. If car A is next to car B, they need to interact spatially, regardless of who is first in the list. And now for the innovative way of using block attention. To fix this problem, the authors introduced block attention. If you look at the attention mask diagram here, the green represents standard causal attention, which only looks at the past. Red represents the innovation. They group all tokens belonging to this current time step into a block. Within this red block, attention is bidirectional. Every object slot can talk to every other object slot. This allows the model to have full spatial reasoning about the current scene, while the green area ensures that we cannot cheat by looking into the future. So now, how does the model actually drive then? Once the scene is processed, how do we get an action? The goal, of course, is to predict future waypoints. The authors tested two heads for this. The first one was quantization head. This treats driving like language modeling, discretizing coordinates into bins and predicting them one by one. And then for the GRU head, this uses a gated recurring unit to regress continuous monoids directly from the transformer output. And how do we test these two different approaches? The experiments showed a clear winner, the GRU head. It turns out that while discrete tokens are great for understanding the scene, they are too chunky for control. Driving requires smooth continuous output. So the final architecture is a hybrid. It thinks in discrete tokens, but it acts using a continuous GRU regressor. And then how is the learning achieved? To train this system, we use a weighted sum of two loss functions. First is imitation learning. This is standard behavioral cloning, minimizing the distance between our predicted waypoints and the expert driver's path. Second, and unique to this paper, is auxiliary forecasting. We force the model to predict the future state of the slot vectors. We ask it, where will the slot be in 2 seconds? By minimizing this loss, we force the model to learn vehicle dynamics. If it can predict the future slot, it proves it can understand the physics of a scene. And now on to the experiments, to see what results we actually got. So for the setup, we evaluated the model in the Carla simulator using the challenging longest 6 benchmark. We computed the CarFormer against the scene level baselines, AIM, BEV, and Roach, which use pixels. And for the object level baselines, which is plan T, the metrics are the driving score, the infraction score, and the route completion that we introduced to test and see which model actually comes out on top. So for the quantitative results, the first finding is that if you look at the bottom section, CarFormer with slots achieves the highest driving score of 74.89, outperforming all pixel-based methods. The second key finding here is that by comparing CarFormer to Plan T, the scores are similar. It's about 74 to 73. But looking at the variance, CarFormer's variance of 1.44 is much better than Plan T's at 2.97. This proves that the learned slots are significantly more robust and stable than manual attributes. And then for the third finding that we can see here on the slide, the oblations show that removing block attention or forecasting causes the infraction score to worsen, proving that those technical contributions are necessary for safety. Now, on the effect of slot extraction, we also analyzed the perception bottleneck in Table 3. Since the car is blind, if the slot extractor fails, the number of slots matter. Increasing the slot count from 7 to 30 drastically improved the driving scores. We also found the model initially ignored small objects like bikes. By manually enlarging them, the input, we forced the model to pay attention, boosting the score to 74.89. To validate the world model claim, we measured the forecasting accuracy in the Table 4. We compare CarFormer to an input copy baseline, which assumes the world is frozen. At time t plus 4, the baseline fails. ARI drops to 0.41, as we can see. CarFormer maintains a much higher accuracy of 0.54. This gap proves the model isn't just copying the present, it is successfully simulating the movement of traffic. So, now on to the conclusions, the limitation of the work presented here, and what can happen in the future to see how we can improve and actually reach full self-driving. The main limitation that we find nowadays, and is also present in the paper, is the dependency on Savi. This is a decoupled two-stage system as previously discussed. The driving policy is entirely dependent on the pre-trained slot extractor. If Savi produces a false negative, meaning it misses a car that exists in the world, CarFormer is completely blind to it. There is no feedback loop allowing the driver loss to correct the perception model. So in this case, when a car is ignored, it can lead to a fatal mistake, which is definitely not ideal for self-driving. There are also some other limitations which are very meaningful in our case, which has to do with the small objects, as we've seen before, and maybe some complex dynamics of our world. The fact that the authors of this paper had to manually enlarge bicycles, for example, as mentioned, and the input data to get the model to see them, is a significant weakness. It suggests that learned slots are not yet sensitive enough to small safety-critical obstacles without manual heuristics. Furthermore, the model creates hallucinations, as with a lot of models nowadays, in uncertain areas, which can lead to some erratic driving behavior. So, about my thoughts on the limitations, I would say that there is also the privilege setting, which is that the paper uses ground truth BEV maps. This is a very privileged approach because in the real world, generating these maps from cameras can be very noisy and error prone. The paper does prove that slots work if you have a perfect map, but it does not prove that they work on real sensor data. And another limitation is the lack of planning. The forecasting is currently just predicting the natural evolution of the scene. It doesn't perform conditional planning. A true autonomous agent should use these forecasts to simulate different actions. So what would happen if I chose to accelerate, or what would happen if I just choose to brake, rather than just limiting on a single path. Rather than just actually imitating a different path, I'm sorry. And now about what can happen in the future to reach full autonomous self-driving. The first step, I think, should be end-to-end extraction. We need to extract slots directly from the camera sensors and bypassing the perfect map assumption that we currently do take. Secondly, we should move forward with model-based reinforcement learning. Instead of just predicting the next waypoint, we should use the slot forecast to plan complex maneuvers, leveraging the world model capabilities that we already have in order to choose what is the safest long-term action and not just what's the safest next action, for example. And I think this concludes our presentation on this paper, which was a very good way to get familiar with real-life paper and research for our computer vision class. Thank you very much for your attention.